also from my side in this webinar. A webinar where we try to discover the flexibility potential of industrial plants. And indeed, Fernando already mentioned, we developed in the project a methodology to valorize and quantify the flexibility, the demand-side flexibility for industry. And we called it, during the project, we called it ProFLEX. Good. Maybe on the next slide, quite important to mention is that we already gave a webinar on this topic where the ProFLEX methodology, or we called it the simplified methodology in the beginning of the project, is explained in more detail. So in this webinar is actually the next step where we want to talk about results we could achieve with that ProFLEX methodology. On the other hand, I think it is important that I saw in the participant list that there are quite some people which did not participate in the previous webinar, so it's important that we remind you what this ProFLEX or simplified methodology is about, but the focus will be on the results. If you get a bit lost on the way on the actually simplified methodology or the ProFLEX methodology, you can go to the recording of the previous webinar, which you can find in the link which is in this slide, which you can find later on in the PDF version you will receive. Okay, Fernando already introduced the project a bit. The whole concept of the project is that we are facing a new energy revolution, lots of renewable energy becoming available on the electricity market, and on the other hand, which comes with certain challenges, and on the other hand, we see a complaining industry complaining about raising costs of energy and electricity. What we try to do in this project is bring them together, see whether we can create win-win situations between the energy-intensive industry and the renewable energy sector. That's the broad goal. It is a European project. You see the partners here at the bottom of the slide. It's a mixed consortium of academic and industry partners. Originally, the goal of the project was aiming, focusing on the chemical industry, the non-ferrous metals industry, the steel industry, cold storage facilities, and water treatment plants. In the meanwhile, we learn, and we have been confronted with a very responsive paper industry sector. So on the go during the project, we took them on board as well. We tried to cover the following countries in our project: the UK, France, Belgium, Germany, Italy, and Spain. Good. Maybe the right time to give you a rough outline of what we are going to talk about today. First, a quick introduction on demand response. Probably most of you know already what it is all about, but maybe it's interesting to have a short recap. Then I'm going to start with a calculation example to show you what it actually is all about. Then I am trying to explain to you why we need something more simple, and that's what our ProFLEX methodology will be. Then we try to apply that in the original example, and we show some further results in case studies we did during the project. And at the end, I hope to come up with some interesting conclusions. Good. First part, demand response. I think it is not a big secret that our electricity system is changing a lot at this moment. In the past, it was relatively simple. You had the traditional generation units, you had the customers, you had a grid in between, and balancing demand and production was in the hands of the traditional generation units. If there was less demand, the production facilities were turned back a bit or turned up when there was more demand needed. Now, with the upcoming renewable energy, this became a bit more tricky because, one, the number of electricity producers exploded. In the past, a couple of hundred at the traditional energy sector. Now there are thousands small little renewable energy sources in the grid, which are way less controllable. So That's one thing. A second thing is that the grid was never designed for these bidirectional electricity streams. So in the past, it was typically the electricity flowing from the high voltage grid to the small, to the low voltage distribution grid parts. Now you see also flows going the other way around. I tried to show that in this slide, and you can have, for example, issues as grid overload situations. Now, the traditional way to cope with this would be adapting the electricity production. That would mean, in this case, curtail the wind turbines of the solar PV panels, which is a bit of a pity. An alternative solution, and that's what demand response is all about, is that instead of trying to control the electricity production, you are going to look whether you can find parties which can absorb that electricity at that moment in time. And that activation or control of the demand instead of the production side is called demand response or demand side management. Now, this is a very simple example, very much focusing on renewable energy, but you can find quite a couple of variants where the industry can help support the electricity grid. We come back later to that. Now, quite important to stress for me always in this kind of presentation is that this is not just an academic invention. In the Energy Efficiency Directive of 2012, the European Commission clearly indicated that they see demand response as an important tool for the further growth of our energy system, mainly for the incorporation of high shares of renewable energy. So in the directive, it clearly states that member states shall promote access to and participation of demand response in balancing reserves and other system service markets. That's going on at the moment. It happens a bit at different paces in the different countries, but this becomes more and more important. Okay, that was my brief introduction. Now I am going to back to this to the previous slide again. If you look here in this slide to this company here, this company at this moment is helping the grid. And what it is all about is, in the methodology we are going to discuss, is this company should not do that for free. They try to support the grid, but they want to get a remuneration for that. And that's what we call demand response business cases. How can companies today make money by supporting the grid? How can you identify which flexibilities are in this company and how much money they can make with it? And that's what this presentation is all about. Good. Let me give an example. We did in the project, we did a number of case studies. One of the case studies was in a foundry. And if you want to calculate for them how much money they can make with their flexibility, you have to do a couple of things. The first step is identify whether that kind of flexibility you are looking for in the process is really there. That's the very first step. So answering the question, which industrial processes or equipment contains demand-side flexibility? During our audits, when we go to these companies, we do this in 3 different steps. The first step is we ask the companies themselves, do you think yourself that you have that kind of flexibility we are looking for? We do that with a questionnaire. A second thing is, the second approach is we look from the top down. We are going to analyze their electricity consumption patterns, look whether it's like really flat or there are lots of variations in it. That's another way to look at the industrial process, and maybe we can identify other sources of flexibility there. The third step, and that's a quite important step, is what do we see bottom up? We go visit the site. We discuss more. It's typically like it takes a day. We discuss with the plant operational people, with the energy manager. We do a tour over the site, focusing on what is there, and we bring all this information together in order to come up with what could be flexible in that particular company or on that estate. In order to go further with our example, in that foundry I am talking about, we came to the conclusion that an induction furnace, which is a kind of buffer between the, wait, I'm going to put the pointer on again. So here you see an induction furnace, which is an electrically heated buffer of liquid cast iron, which is in between the main furnace and the pouring ladles, which are used to pour liquid iron into casts. Now this is a big buffer. It contains like a couple of tons, up to 10, 15, 20 tons of liquid steel. And it is kept on temperature by means of electric induction heating system. And the temperature of the liquid iron should stay between 1480 and 1520 degrees Celsius. That's a source of flexibility because the mass is enormous. So if the temperature is 1500 degrees and you switch off the heating for a couple of minutes, it will cool down, but that will go very slowly. So it can handle a couple of, in this case, easily an hour being without electric heating. Of course, you have to catch up later in the process. So that's the process we identified as flexible in that foundry. The second step is you identified it. The next step is you have to quantify how much flexibility is in that furnace. And what we do in practice is we create a kind of simplified mathematical model of that furnace, which describes the relationship between electricity you put into the furnace and the actual temperature in the furnace. This is depicted in the figure here. You see here the power consumption of the furnace is really low, and you see here that the temperature is going down. At some point in time, you increase the power consumption, that happens here, and you see that the temperature rises. So that's what we model. That's what we call the quantification step of the flexibility. That's step number 2. Then we go to the third step. The third step is the valorization of the flexibility. At this moment in time, we still don't have a clue how much money we can make with that flexibility. In this step, we are, in this particular case, there are quite a couple of possible business cases for demand response. If you want to have details of all kinds of business cases, I'm not going to do that in this presentation because that would lead us too far from the discussion of practical results in the project. I refer to the original presentation I gave, where I give the reference of in the beginning of this presentation, where it is more elaborated which possible business cases there are. The business case we look at here is buying electricity at the day-ahead market. Large industrial customers have the possibility to buy their electricity on a day-ahead market, which has a variable price which varies hour per hour. In the top graph here, you see the variable price as function of the time. So there are typical moments, typically in the night, where the electricity only costs 30 euro per megawatt hour. There are other moments in time, for example here, that will be probably in the morning peak. There the price is about 80 euro per hour. And the whole trick, of course, is to try to switch on your furnace. This is the electricity consumption of the furnace is line. You try to switch on your furnace at the moment that the electricity is really cheap. And you try to switch off your electricity consumption at the moment that the electricity price is very high. At the lower plot, you see the variation of the temperature in the furnace. So you see it nicely stays within the limits which were depicted by the company. It stays nicely between 1480 and 1520 degrees. But by doing this, you can make money. Suppose you would not do that. You could say like, okay, we are going to apply an average electricity consumption, in this case of 160 kilowatts, to the induction furnace. That would result in an electricity cost of about 73,000 euro per year in this particular case. That's what we call the reference case. The second case, we are going to do the optimization. So we are putting our model into a mathematical optimizer, which is going to select these optimal moments where to buy electricity and try to reduce the electricity consumption. And that optimizer comes up with the cheapest possible solution, which is 65,000 euro per year, or in this case, this company could make a profit of about 8,500 euro per year by clever buying electricity on the day-ahead market. Okay, that's the 3 steps we did for that company. So they know now what the potential value of that induction furnace in their process is. The next step is I'd like to explain to you why we need something more simple, why we need this ProFLEX methodology we have been working on in our project. You see, in the 3 steps, which we discussed earlier, identification, quantification, and valorization, with our ProFLEX approach, we can't simplify everything. The focus on the simplification we can do is in the quantification step and in the valorization step. We can not help you with that identification step. That identification step is not so easy to automate. Of course, you can try with questionnaires and so on, try to make it easier for third parties to do this kind of audits, but that's not what we aimed for in the ProFLEX methodology. In the ProFLEX methodology, we are aiming to make the quantification and the valorization step easier. Why we would like to do that is, as you can imagine, if I described the steps earlier, making a mathematical model, going on site, using optimization software and so on, that's a quite time-consuming process, which costs not only time, but money. What we have seen in practice during the many years as an institute we do this kind of audits, what we have seen is that building up interest in demand response in many companies is a long time-consuming process. And what we have seen, for example, for a particular company, we did a first audit, I think about 4 or 5 years ago, and that number, after all, was not so accurate, but it was like a first number the believers in the company still use today to their management. You see the value is there. So if you want to make steps forward with demand response in the industry, it is very important in an early stage to have an order of magnitude estimation of that value. That's more important than having a super accurate value with a very fancy audit, which is actually too expensive in the first place, so the company will never know what the potential value could be. So for us, that's a very important step. So with that ProFLEX methodology, we want to be cost and time efficient. Our statement is that an order of magnitude accuracy is good enough. If we can get it right to about 20-30% accurate, that is good enough. And I'll have examples later which clearly show that 20-30% is good enough. And then, very important, what we want to get rid of is that specific modeling and optimization knowledge, because that's not really in reach of all kinds of companies. If I give the example of a consultancy agency offering services to the industry, for example, to do energy efficiency audits, they could maybe add energy flexibility audits to their portfolio, but typically optimization, tooling, specific modeling knowledge is not within their reach. So that's what we want to get rid of in that simplified approach. What needs to be changed then? Okay, I understand this picture quite pops up here in this presentation and looks maybe a bit complicated. Again, it is way more elaborated in the previous webinar we gave on this topic. If you want to do a business case calculation for demand response, actually you need four things. You have to choose the right business model. There are quite a couple of possibilities. The head market optimization, you can go to the reserve market, imbalance optimization, contract optimization. There are quite a couple of possibilities there. Secondly, you are dependent on the regulation of that particular market in that particular EU country. So that's important information as well. You need to have the market data. You need to have a flexibility model. Then you need a calculation method by means of an optimizer, and then you can calculate your business case. Oops. Okay. So the two steps we want to simplify is that modeling step and the optimization step. And the flexibility modeling step we are going to replace by what we call in the ProFLEX methodology mapping on a reference process. I'll show you with an example later what we mean with that. The second thing, we want to get rid of that optimizer, and that optimizer we are going to replace by normalized business case graphs. I understand at this moment in time that sounds very abstract. That's the reason why we are going to jump to an example later on, which will make that more clear. So if we start from our industrial process, the first step we do is we are going to normalize this industrial process to reference units. It will become clear in the example. Then we, so that it is in 1 megawatt, we can define a 1 megawatt equivalent. Then we select the right business case graph. A business case graph is made for a specific business case and for a specific reference process. Select the right value from it, scale back, and we should have the value. And I completely understand if you're completely lost at this point in the presentation. That's the reason why I add now my example again. Now we are going to apply that ProFLEX approach again to that initial example of the induction furnace in the foundry, and I hope it will be a bit more clear for you what we try to do here. Good. My statement is that an induction furnace is a bit like a battery. You can, at some moment in time, push an awful lot of energy in it, which in such a way that you kind of charge the battery, or what that means for the induction furnace is you warm up the liquid metal in the induction furnace. Or you can discharge your battery. Discharging your battery is the same as switching off your power in your induction furnace, and automatically some power will flow out of the induction furnace and it will cool down. Now, if you look carefully into the graphs we have been looking at earlier, so the graph here where you see the buying and where you see the clever buying of electricity on the day-ahead market, if you take the blue line as a reference, you see quite well that at the cheap moments you try to increase your electricity consumption. At this point you try to decrease your electricity consumption. If you use the blue line as a reference, you can see that a bit as a battery which tries to buy electricity with high power at the cheap moments and tries to sell it again on the market at the moment that the electricity is a bit more expensive. So
sorry, Chef. Maybe you can use the pointer to guide us through.
Okay, did I switch the pointer off?
It's just over here. Let me check.
Yeah. Is the pointer now moving?
No, you should click on the screen. Now it's moving. Yeah, now it's moving. That's it.
Okay.
Thank you. Thank you.
Thank you, Fernando. I thought I was showing the pointer, but I was not, apparently. Okay. Back to my battery example. So you see here at this point that the electricity is a bit cheaper. That's the point where you try to charge your battery. This is the point where you try to discharge it. You see that battery behavior nicely in the optimization results of the induction furnace. So you can mimic an induction furnace as a kind of battery with a charging power of 0.4 megawatts in this case, and a discharging power of 0.16 megawatts. Also, there is a kind of battery size involved as well. We can, in about 1 hour, we can put like 0.41 megawatts into that virtual battery. So the virtual battery size we are talking about for our induction furnace here is about 0.41 megawatt hour. Now, what is the trick? The first trick is we normalize everything to 1 megawatt equivalent. So by applying a scale factor of 2.28 on the original numbers we identified in the previous plot, we end up with the numbers here: 1 megawatt input power into the battery, an output power of 0.3 megawatts, and a virtual battery size of about 1 megawatt hour. What we have been doing now, of course, we cannot make pre-calculations of all kinds of industrial processes beforehand, but since we consider our battery as a kind of reference process, we pre-calculated the value of the business cases and put it in a graph. That's what you see in this figure here. What you see in this figure is the value in euro per megawatt per hour, which you see here on the vertical axis. You can make with your flexible process for a battery with a size which is indicated here on the x-axis. This is a 1 megawatt hour battery. This is a 10 megawatt hour battery. And this is the output power of the battery. So for 0.1 megawatt output power, the value is less. If you can really draw a lot of power out of your battery, you can make more money of it. So what we did is we look up the right value in that graph. We zoom a bit into that. So we remember we had a battery size of about 0.941 megawatt hours. The output power was 0.336. So you see that in this graph we can read a value of 2.18 euro per megawatt per hour. Sounds still maybe a bit abstract. What's the next step is that we scale that back. Instead of that 1 megawatt input power, we scale it back to the original value of 0.43 megawatts, and you see all the values scaled together. So the value we could make with that virtual battery would be 0.958 euro per hour. Okay. As you remember, a couple of slides ago, we did a full analysis, a full-blown analysis, a full-blown optimization, and we came to the conclusion that we could make a value of 8,472 euro per year. If you take the value we get from this graph, 0.958 euro per hour, and multiply it by 365 and 24, we can see the value per year. Then you see that these values are very close to each other. It sounds maybe a bit complicated. The main thing you have to remember from this, if you didn't get like all the complex details, is that just by looking up some values in a graph, we were able to replace a complex mathematical modeling step, and we were able to avoid optimization tools in order to come up with a value which is very similar to each other. I hope after this example it is a bit more clear how that ProFLEX approach works. The case study I've shown you is one of the case studies we did in the context of the European project. We did a couple more. So we did a case study in a foundry. We did a case study in a paper industry, in the wastewater treatment, and in a distribution center which includes a cold store. These case studies were executed in Belgium, Germany, Italy, and the UK. I keep, on request of these companies, I keep the company names anonymous, so I was able to share the values under the condition that I don't share the names of these companies. Another case study we did was in the paper industry. The paper industry case we did at a paper mill of a large worldwide player in the paper industry. And they were already very advanced in terms of demand response. They already have they offer already reserves to the electricity grid. They already source the electricity on the day-ahead market. So they already did quite a bit. On top of that, they have a CHP, combined heat power facility, which can produce electricity and heat based on gas. But they still have issues with large imbalance volumes. That means that every large company has to nominate their electricity consumption the day before. And if they, during the day, deviate from that, they have to pay imbalance fees. And the question of the company was like, do you see, suppose we add electric boilers on our facility, would that help to get our imbalance cost under control? That's what we try to do for them. Now, what is the idea? That's what I try to show in this figure here. They have a certain heat demand, which is relatively constant. That's what you see at the right-hand side of the picture here. And they can produce it. The idea is that they can produce it in two ways. Either you do it with a gas boiler, or you do it with a hypothetical electric boiler. So the trick is, if the imbalance price is lower than the gas price, it makes sense to switch on an electric boiler instead of the gas heater. That's the idea. So based on the historical imbalance volumes and prices of 2016, we try to calculate what that value could be for them. The conclusion was that in ideal conditions, on their total electricity cost, they could save 1.7%. They could get their electricity cost 1.7% lower if they would invest in a 10 megawatt electric boiler. Now, I have to be very careful. You have to be very careful with the interpretation of that value. It's a theoretical maximum you can achieve. In practice, we are convinced that value will be significantly lower because imbalance prices cannot be predicted so well. To put that a bit in perspective, the values are compared here with the investment cost they should do for that boiler. So the 1.7% mentioned here corresponds more or less with a 300,000 euro savings per year. And if you see that the investment cost for an electric boiler is about 60 to 130,000 euro per megawatt, you have an idea how this relates. So in theory, a payback time of about a theoretical payback time of 2 to 3 years would be possible if the 1.7% could be reached. In practice, it will be closer to like 10 years. And it's up to the company to decide what they want to do for that. That was the first case. Now the bad news comes. Our ProFLEX approach did not work there. Why was that the case? Because the reference battery model does not work in this particular case, because it is a switching between two commodities, between the commodity electricity and the commodity gas. There is no energy buffering involved at this point. So at this moment in time, the conclusion was ProFLEX was not suitable for this particular case study. Doesn't mean that it is impossible, but we'll come back to that in the conclusions. The third case study we did was a wastewater treatment case study. We did an audit in a large wastewater treatment plant in a large European city. Wastewater treatment typically goes together with lots of biogas production. The biogas production, which they then use for the digestion for the biological processes in the wastewater treatment plant. And so they need heat, and what they do is the biogas is used in CHPs or in micro turbines to produce as well heat and electricity, because their electricity costs are quite high. They need lots of aeration of the wastewater with large compressors which blow air through the to the water which has to be treated, and that's one of their biggest costs. Typically, the electricity cost is about 10 to 25% of their operational cost. The site which we investigated on top had wind turbines, and what we tried to do in this case is see whether the local produced renewable energy could be used in a more optimal way to make additional, to reduce their electricity cost, basically. This gives a top-level view of the plant. What you see is, first, biogas production, which comes in here at the left-hand side, and you have a biogas buffer. The biogas is used by a CHP, which produces electricity, and it produces, the red line is heat. There's also a gas turbine. The gas turbine does exactly the same thing. It produces electricity and heat. There's another way to produce the heat. That's by means of the gas boiler. So they have a constant heat demand. They need electricity for their wastewater treatment, which is here, which has some flexibility as well. And there are wind turbines which can produce electricity which can be used by the plant, but if there is too much electricity, they have to inject it in the grid. Now, it sounds a bit complicated. The whole trick exists of, if there's lots of wind available, you want to avoid to inject a lot in the grid because you don't get a lot paid for that. So what you try to do is try to use more electricity and reduce your gas consumption. When there's not a lot of wind available, you do the other way around. Then you have to buy a lot of electricity. So what you do then is you use your stored gas to produce more electricity with your gas turbine or your CHP in order to reduce the buying of the electricity. Now, we split this up in three subcases. A first subcase where we only consider the flexibility of switching between the gas turbine, using the gas buffer and not the flexibility in the electricity consuming process here. A second subcase where we only use the flexibility here in the wastewater treatment and we consume a constant heat production, and then we tried to combine them together. The overall results you see here. I'm not going to go into details because I see it's already like 20 to 3 and I want to head to my conclusions. The main point to remember is if we do a full optimization in the three subcases, you see that these are the values that company could earn with their flexibility. So in case A, that would be 4,500, case 2, 7,900, 12,000 in the combined case. With the ProFLEX approach, we ended up with numbers which are in the same order of magnitude. 5,000 instead of 4,500, 8,400 instead of 7,900, 15,000 instead of 12,000. So it deviates in an order of magnitude. It depends a bit from case to case between 6 and 25%. So the conclusion for the wastewater treatment plant was that actually only 1% theoretical electricity cost reduction could be achieved with the flexibility which was available there. Of course, keep in mind that's for this specific wastewater treatment plant. That does not mean it all depends on the sizes of buffers and the installed capacity of CHPs and micro turbines, how the actual value is. So it's not like a general conclusion for all wastewater treatment plants. Secondly, we saw that actually, and that was a bit to our surprise, that the flexibility in the wastewater treatment, so the variation of the electricity consumption, gained more for them than the switching between the electricity or gas commodity. For the ProFLEX methodology, we came to the conclusion that the generic battery model approach still works reasonably well. And secondly, that a combination of combining several flexibility sources, which actually the simplified methodology or the ProFLEX methodology was not developed for, it resulted in an overestimation of 25%, but we still consider that as a first estimate quite reasonable. Let's be honest, 1% is the value that company could save on their electricity bill. If you're 25% wrong, that would mean it is either something like 0.75 or 1.25. That's still the same order of magnitude. Then the last case study was a large distribution center. A distribution center which basically it's a distribution center of a large supermarket chain which has 600 supermarkets in their home country. And this supermarket chain is, the logistics are done by 20 distribution centers, which typically have refrigeration. So what we asked them beforehand in the questionnaire is, where do you think that you have like electricity flexibility? Their answer was, well, we are convinced that it is in the refrigeration system. After the audit, we found two more flexibility sources, namely a battery charging station and the emergency generators. The refrigeration system, we came to the conclusion that they could make, we modeled that, we made a quite simplified approach with the ProFLEX methodology and came to the conclusion that they could make about 6,000 euro per year with that. For the emergency generators, that's another story. That's something they forgot to mention in the questionnaire, but there the order of magnitude of money they can make is about 100,000 euro per year. Then the battery charging station, that's something we investigated as well. We came to the conclusion that, battery charging station is used to charge the batteries of the little trolleys, which transport pallets in the distribution center. And they always have like about 40 batteries on charging, which needs to be swapped. So we could model that with the ProFLEX approach as well, and came to the conclusion that the value is more or less 1,200 euro per year. Now what's important in this case is that we only used the ProFLEX methodology here, and we did not a validation on these numbers, and probably there is maybe a mismatch of 10, 20%, we don't know because we did not validate that. But the very important thing is that we can quickly identify the orders of magnitude. You see immediately from these numbers that the big fish is at the emergency generator and not at the charging station. So although we did not do a validation here, we considered it as a quite interesting case study because it showed that with a very simple approach you can get the orders of magnitudes and direct the company to get the focus right on what they should work on. So that's the second conclusion we had for that distribution center. Okay, some conclusions about our ProFLEX methodology we developed in the project. We used the ProFLEX methodology in 4 use cases. And in 3 of them, we were able to do a validation and to check whether it really worked. The conclusion was that for the foundry, for the induction furnace, it worked really well. For the distribution center, it worked really well as well. The wastewater treatment was more complex, so there the results were a bit more deviating from the actual result. And for the paper industry case, it did not work at all. Important to mention, though, that the ProFLEX, if the ProFLEX methodology or the business case was not good for this particular use case, that does not mean that for the whole sector it does not work. It does not mean that for the whole paper industry there is no business case for that the ProFLEX methodology would work. The main thing is that with the introduction of new reference models, we could get a step further. And that's what you find back in the observations while at the end of the case studies when we were evaluating them. We actually mainly worked with a business case graph for where we used a battery model as a reference. And what we saw, there is definitely some multi-commodity normalized business case graphs missing to make it work, for example, for the paper industry and the wastewater treatment business case. A second conclusion was that complex processes with lots of different constraints are not as easy. A third one is that the mapping step, we came to the conclusion, is not always as easy as it seems. And that concept of that virtual battery, we came to the conclusion that we considered it ourselves as pretty tricky. But after we used it a couple of times, it gets better and better. So that requires a bit of training, and that will be the tricky step in the rest of in the further development of the approach. It works very well to get the order of magnitude right in simple or simplified cases, which has been shown, for example, for the emergency generator or the distribution center use case. Further, we learned that clever combination of a couple of simplified cases works fine as well. I could not show that in this presentation, that would lead us too far, but clever pro rata scaling of different cases gives pretty good results as well. And of course, if the real process matches really well on the reference process, the accuracy is very good. The examples are, for example, in the foundry and in the wastewater treatment, it worked quite well. Good. That was actually more or less the end of my presentation. The methodology at this moment, we are trying to get it to the market. That's part of the project as well. We already had workshops with interested parties. But nevertheless, if you feel addressed or feel interested with the methodology we presented in this presentation or the results, of course, get in touch with us, and we can see what you actually need and whether what we developed maps can be of any use for you. And that's the end of my presentation. Thank you for your attention.